Hi, my name is Chima Jagada. I'm a student at Lisbecker University, and this is my dissertation project. A feasibility study of popularity-based route recommendation using Strava data. In this video, I'm going to walk you through the problem I set out to solve, the system I built, and how I implemented it, and what were my results. Let's start with an overview of the project. Existing tools like Google Maps optimize routes for speed or distance, but they don't reflect which routes are most popular, or they tend not to. And Strava is a fitness platform used by millions worldwide to capture GPS data for various activities, cycling, running, whatever activity. Now, Strava data has been used in existing research mainly as an observational data to study people during when they're active, rather than use it to construct or recommend routes. This could be because of the fragmented nature of Strava segment data. Because it's fragmented, it's not naturally connected into a network. So the question was, is it possible for me to take that fragmented segment data and transform it into a connected routing network that will recommend routes based on popularity? I set for myself four clear objectives. First, to retrieve and analyze the Strava API structure, design a graph-based method for combining the segments using popularity weighting, implement a prototype route recommendation system, and then evaluate whether the visibility of this entire project using route connectivity, construction, and routing performance. Because the focus isn't just whether the system runs, it's about whether it produces meaningful results and where it falls short. My solution works. Um, my solution works in 5 stages. I first start by pulling data from Strava via the API, pre-process that data into a more usable format. Using that now pre-processed data, I build a weighted graph using JGraphT. After which I run Jackstar's algorithm on that graph to find the most popular path based on the weighting that has been attached to the graph. Then using Spring Boot connected to a user interface built in React to be able to display the results. So each stage feeds into the next. So if the data I got from Strava is sparse, it will affect how the graph is constructed, and which in turn will affect the routes. So let me show you the system in action. So here we have the running system. This map view is being done by Leaflet.js on a React front end. On the left panel, we have the various ways we can input a start and end point, the route weights that we can select, and all the components. We have the area we're using is leads, and on the map you can see all the various markers. These markers indicate the various nodes in each of the components. This corresponds to the color codes on the left panel. As you can see, for each of them we have them. So now we're going to focus on the largest component, which is component 0. This is the largest connected component, and it spans over a large area. So now we're going to pick a start point. To pick a start point, we need to first click on the start point button, then decide on a node. We're going to go with this one. This is all the information regarding this node, from the watch components, identification, and last student longitude. It all exists in component 0. So now we're going to pick the endpoint. Click on the set endpoint button and then click on the node. That's all the information regarding that endpoint. Now, if I was to click on the generate route, it will give an error and tell us to select a route. This is just an example of the error handling I implemented for the front end. So now we're going to click on athlete. Just a moment. We're going to click on athlete. What's in the world? Yeah, sorry. I'll generate route. So now, as you can see, we have the visualization of the routes as an orange path, or orange line. And on the left panel, it has updated to show all the information regarding the route, including the segments used, nodes, the segment names, and the athletes count associated to those segments. This is all the information for that route. So this also occurs when you use effort. If you click on effort and then generate route, everything is updated to be based on based on the effort graph, what the segments used, the nodes, the segment names, and instead of the athlete count is now the effort count. Now we're going to combine. This is the same. Combine is a 70-30 ratio combination of effort and athlete. This displays the same as the effort and the athlete count. Let me walk you through some of the key parts of the implementation. Starting with the Strava API integration. So now I created a method called explore segment tiled. This takes a geographic bounding box defined by the southwest and the northeast latitude and longitude coordinates. It then divides it into grid tiles using the grid rows and the grid columns. It takes these parameters and sends a request to the Strava API for each tile. Now, the reason why I decided to go with this tiling method is because Strava segments explore endpoint only returns segments within a limited geographic area at a time. So to ensure that I get a much wider coverage, I divided the target area, in this case leads, into much smaller cells and sent a request for each of those individual cells. The results are deduplicated using a linked hash map. This keys the segment ID and ensures that if the same segment has been retrieved, it's only stored once. Then we have a timer at the end of each call to respect Strava API's rate limit, which is 100 requests per 15 minutes. This is to avoid being throttled. So that is to ensure that we don't get stopped in the middle of retrieving the data. The next important part of the system is the graph construction, specifically build graph. This is the main method that builds the graph. This takes the segment data that we've retrieved and processed and makes it a routable graph. For each of the segments, the method first identifies split points, which are the segment start, endpoints, and any intersection where the segment crosses another. These are classified. With this then become the nodes of the graph and are classified as segment start, segment end, and intersection type, and added to the graph as a vertex. Once the nodes are in place, the method creates directed edges between consecutive nodes. For each pair of adjacent nodes, it calculates the subdistance between each of them and constructs a graph edge object. This is then, after this, the edge weight is set based on the weight type parameter. So depending on what was selected, whether effort, output, or combined, it will influence the type of weight that is attached to the edge. An important part of this graph, of the graph construction, of build the graph construction, is the reverse edge implementation. So this allows that for every forward edge, a reverse edge is made so as to make the graph traversable in both directions, because movement is in it of itself it's bidirectional in nature. The next important code is the root generation. This brings everything together. This takes the start and end coordinates that have been selected from the front end, finds the nearest graph nodes to those coordinates, and retrieves the correct weighted graph for the selected weight. A few early exit checks are done to ensure that the graph is properly loaded. The start and end nodes actually exist in the graph. This is just a bit of error handling to ensure proper root generation. The method then uses a connectivity inspector from JGraphs to inspect the graph and log how many connected components it takes. After which, Jagstar algorithm is applied using Jagstar shortest path from JGraph. If no path exists between the two nodes which are put into the getPath method, it sends an error saying that the nodes are in different disconnected components. However, if the path is found, it iterates over the vertex list to collect the geographic coordinates of each of the nodes along the route. And over the edge list, it collects the metadata for each of the segments, which are name, effort count, output count, distance, and the actual weight, edge weight. All of this is then assembled into the route result object, which is returned to the front end and rendered in as the highlighted path on the map. For if you want to get more details, see the full source code and all the graphs, um, graph implementations, everything, you can find them on my GitHub, which I will also attach to the description for you to check out. Everything is there, and you're welcome to explore the code and give feedback if you wish. So let me now discuss what the evaluation showed. Firstly, what were the results? Successful root generation. The system was able to successfully generate popularity weighted roots. And the inverted popularity based weighting approach that I used was shown to be effective. It rewarded popular segments, using them more than um, less traveled alternatives, because of the lower edge weight in the Jagstar algorithm corresponding more to popularity segments. During evaluation, 25.7% of nodes existed in the largest connected component. This showed that the vast majority of the graph is fragmented into a lot of isolated islands, which made it such that root can only be generated between nodes within the same connected component. Let's talk about this limit, how this affected the entire project, and what are some other limitations. Firstly, data sparity. It is probably the most significant issue of the entire project. The system could not generate more roots, or could not generate roots across different components, because I didn't have a full urban area. And during evaluation, some of the testing relied on a small sample size, so the performance at scale it doesn't isn't it remains unverified. Another limitation was that the study I didn't um, I didn't benchmark the system against other routing systems like shortest distance. I didn't compare them. So it could be a limitation. So now, in conclusion, yes, yes, it is possible to use Strava data to be able to make a route recommendation system, but it comes with its own constraints. And some of the for people that want to work on it, there are various areas you can work on, including data coverage, using a final tiling system, and incorporating temporal data. Thank you so much for watching. And